Okay, hello everyone to today's online seminar on interval methods and control engineering. And it's my great pleasure to welcome today Mohammad Khajenejad. And he's a postdoctoral scholar at the Department of Mechanical and Aerospace Engineering at the University of California in San Diego. And he's a well-known expert in the field of robust control, set theoretic members, applied also to resilient and private estimation, learning and optimization, and especially also concerning applications to control of complex safety critical networks, cyber-physical systems. And yes, without further ado, I hand over the microphone to you, Mohammad, to give your talk on remainder form mixed monotone decomposition functions.
All right. Thank you so much, Andreas, for the kind introduction. And thank you also so much for inviting me for this talk. It's certainly my great pleasure to be here and to talk about some part of my research to this community, which I really feel that a lot of work doing by this community has a lot of alignment with what I have been doing. So again, it's my great pleasure to be here and share some part of my research and learn from your feedback, of course. All right, so let me start with this known fact that cyber physical systems that can be found in more or less all societal sectors are usually subject to different types of uncertainties. So robustness is an important factor in these large-scale cyber physical systems. Moreover, they typically have unsafe regions of operations, so they are safety critical. Further, some of them are subject to different types of adversarial attacks, so we need them to operate in a resilient manner. They usually have a lot of flows of data, which we require them to be protected. So privacy is important, and also they usually have heterogeneous agents with local communications. So at the end of the day, we want them to be considered as network setting and work with network cyber physical system. So having these in mind, maybe my big research questions has been, can we leverage some dynamical systems properties that help us to obtain robust, resilient, distributed, and private autonomy? And then particularly in this talk, I'm going to talk about some of these properties and in particular, the interesting mixed monotonicity property that enables us to do guaranteed reachability analysis and resilient estimation as backbones of safe and secure autonomy. And I'm pretty sure for this audience, I don't need to really talk about a lot of applications of reachability analysis and resilient estimation in cyber physical systems. You're more familiar and aware than me of these applications. So then I will start with mixed monotonicity and how we use this interesting property to design some specific form of decomposition functions, which I call them remainder form decomposition functions. And then I'll talk about some of applications of these type of decomposition functions in set valued state estimation, interval observer design, and resilient estimation in cyber physical systems. And then at the end, I'm going to share some future visions of this mixed monotonicity and the things that I will be interested in doing in future. All right. So I'm going to start with introducing these remainder form decomposition functions. And to that end, consider a dynamical system like a car, a vehicle with its states as positions and velocity, and then we lump all sources of bounded uncertainty as this W vector, and the dynamics of this system can be modeled as a a difference equation or a differential equation, as can be seen. So because of all these uncertainties, the initial state of this system is uncertain. We have an initial set as the initial possible positions and velocities of this car. We want to propagate it through the dynamics and capture all possible values of states of this system through time, which we call it reachable tube or reachable set of this dynamic systems. And why do we care about it? Because, for example, if we care about the safety of this car, then we want to take the intersection of this reachable tube with the unsafe regions of operations of this vehicle, make sure there is no intersection between them, and verify the safety of this system, in addition to a lot of other applications. So if our system was a simple linear system and our initial set was a simple like interval or hyper rectangular, then all we needed to do was to just propagate the vertices of this initial set through the linear dynamics and get the reachable set. However, as you know, for nonlinear systems, this computation could be very hard. We might end up getting a very weird, non-convex, even disconnected reachable set, and very most of the time very hard to be computed exactly. So to tackle this problem, there have been several approaches. One of them is to do it through inclusion functions. And that is basically to find a possibly tight enclosing box or interval to this reachable set. And as you might be familiar, using interval arithmetic, there have been very effective, computationally effective ways of computing these inclusion functions and including sets with slight differences. They are very efficiently computable, but they can be also very conservative. More that have been worked suggested based on mixed monotonicity, and people try to propose mixed monotone forms of inclusion functions or decomposition functions. So now is a time to maybe formally talk about this mixed monotonicity and decomposition functions. Hopefully you are motivated enough now. All right, so mixed monotonicity. So given a discrete time system with the vector field F from Z to Rn, and Z is the augmented state space of state and noise, Fd, which is defined from the higher dimensional space of Z times Z to the same range of F, is called a discrete time mixed monotone decomposition function with respect to F if Fd satisfies three conditions. First, Fd of Z and Z coincides with F of Z, which means that F is embedded within Fd. The second condition is Fd is monotonically increasing in its first argument and also is monotonically decreasing in its second argument. In the continuous time, almost the same, with the slight difference that this second condition only needs to hold for off-diagonal arguments, and that is due to the subtle difference between monotonicity discussions in discrete time versus continuous time systems. Okay, and then if such an Fd can be computed for an F, then that Fd is called a decomposition function, and that system is called mixed monotone. Okay, and then this, just to mention, these decomposition functions are not unique. There have been different suggestions for different types of decomposition functions for a system, for a given F. given any decomposition function for a system F, an n-dimensional system F, we can always compute a two n-dimensional like this, which we call it embedding system, and it is almost immediate that to be shown that the states of this embedding system frame the state of the original system from below and above, which is called the framer property of the embedding systems. Okay, just to mention some of the recent suggestions of these decomposition functions, here, the group of Professor Sam Coogan from Georgia Tech proposed one specific form of these decomposition functions, which they call it optimal, which is technically computing the minimum and maximum of the original function f in each dimension over the given interval, which is, yes, of course, it is tight and it is optimal, but if these min and max problem can be tractably solved, which is possible for some specific classes of systems. Another famous suggestion for these decomposition functions is the one that is suggested by the group of Professor Nechmi Ozai from Michigan, which is based on some specific shifting of the original function towards some of the vertices of the interval domain. And it is very computationally efficient, can be applied for almost all classes of systems, but is not necessarily the tightest one. So this, inspired by this design, we were thinking if this is the only way of shifting systems to get the compute the decomposition function. Can we do other type of shiftings to obtain possibly better decomposition functions? And what is the best way of doing it? And that gives us this notion of remainder form decomposition function, which I'm going to talk about it now. So to start, it is not easy. It is not hard to see that for a given f with bounded Jacobians from below and above, we can always decompose f into two components: a linear component, which I call it linear remainder, and a nonlinear, in general, nonlinear mapping, which I call it Jacobian sign stable mapping. And Jacobian sign stable basically means that this Gx is also monotonically increasing or decreasing in each dimension. Okay, it's always doable, and it can be done in multiple ways, given the bounds for the Jacobians of f. Okay, then we have two components for this f and an interval domain. So the linear component can be tightly bounded from below and above, using a very famous result in this like interval literature, and also the JSS mapping. Since it is monotone in each dimension, it is easy to follow and see that the maximal and minimal values of this G over this interval domain will attain in some of the vertices. Okay, so with this we can find bounds for this linear remainder and also this JSS mapping separately without any need to solve any optimization problems. And then by just adding these two bounds, we compute upper and lower bounding functions for this nonlinear function f, which are proven to satisfy all the conditions of decomposition function. So they are decomposition functions. And then, as you can see, this directly gives us a family of decomposition functions, because this decomposition is not unique, as I mentioned. Okay, so a couple of technical things that you might ask. First, You might ask why I consider just remainder, linear remainders. Why not an arbitrary remainder? And the answer is we showed that for any arbitrary remainder, there exists a linear remainder that is as good as that arbitrary nonlinear remainder. So we really don't need to worry about all classes of remainders. We only need to search over linear remainders. The other question that you might ask is, okay, we had multiple ways of choosing these linear remainders, and actually there are infinite number of taking those linear remainders. Is the computational tractable? And the answer is yes, because we again showed that there is only a countable finite set of slopes that we need to search over to capture all possible cases. And with that, we have just a finite supporting set to search over, and then we can easily search over by enumeration. We can search over that set and find the tightest possible decomposition functions from below and above. Also, we showed that we really don't need the Jacobians to be bounded from both sides. We only need them to be bounded from one side in each dimension. Moreover, this design is also applicable for non-smooth systems using generalized Clark derivatives instead of usual different derivatives of the system. And we can even apply them for discontinuous vector fields if they have finite and countable jumps. And finally, we showed that design from the group of Professor Necmiye Ozay is a specific one of these decomposition functions in this family that we introduced, but it's not necessarily the best of them. So as a conclusion, the remainder from decomposition functions outperforms the one that computed by that group. Okay, so this was a brief introduction of these remainder form decomposition functions, but what do we care about them? Because they have evaluations, which I'm going to talk about them now. First, we can apply them for set-valued state estimation. So as I mentioned before, given an original n-dimensional system, we can, using these remainder form decomposition functions, we can compute a lifted 2n-dimensional embedding system, which can be shown that the states of this embedding system frame from below and above the state of the original system. And this can be directly applied for unconstrained reachability. So given any dimensional system, we can compute these 2n-dimensional embedding system and directly find the states of this embedding system, which directly gives us framers for the original system. We applied it to several systems. For example, this Van der Pol system, and as you can see, the reachable tube of this remainder form system, the blue boxes are tighter than all the other tractable ones, and they are only worse than the optimal ones. And the optimal ones were the ones that are based on solving some optimization problems, which can be solved here for this simple system, but it's not doable for a lot of other complicated systems, which we'll see later. Okay, this was for unconstrained reachability or state estimation. However, as you know, in practice and in real applications, we usually have constraints, observations, and measurement sets on top of just our state equation, which we want to leverage this new piece of information to refine our propagated sets. So technically what we want to do is that after computing this propagated set, now we want to find a subset of this propagated set such that if this observation function applies on that, then it falls into our observation set, right? Which this operation is called like set inversion in general, or refinement or update step in the language of state estimation, which is in general, which is a hard operation. So it turns out that using these decomposition functions, we can handle this problem as well. And the idea is to apply these decomposition functions on the observation equation. And by applying that, we can rule out sub-intervals of this propagated set, which is proven to have empty intersection with the observation set. So by doing that and then using bisection, we can rule out those type of inconsistent sub-intervals of propagated set and design a tractable algorithm that can handle this set inversion algorithm. And combining this with that propagation step, now we can do constraint reachability for a lot of classes of nonlinear systems. And now we're able to apply these embedding systems and decomposition functions to do constraint reachability, for example, in this NASA generic transport model, which is a quite complicated system. And as you can see now, the reachable tube outputted by this remainder form decomposition functions are tighter than the ones that are obtained using other tractable approaches. All right. Then how about if you have more complicated sets, such as polytopes? Can we still apply these mixed monotone decomposition functions to do propagation and also set inversion for, let's say, polytopes? The answer is yes, and the idea is here. So you are familiar with traditional representations of polytopes as the vertical representation, the representation using hyperplanes. More recently, there have been other representations of polytopes using constrained zonotopes or zonotope bundles. And a zonotope is simply an affine transformation of an interval, basically. So this gives us the idea. Given any point in a polytope, we can always find a generator, this capacitor, which lives in an interval, and there is an affine transformation between that generator and that point inside the polytope. So using this affine transformation, plugging it into our original function, we end up having a new function with respect to this generator, where generator now lives in some interval. Now we are very happy because we are in the space of intervals. We can apply all our existing approaches, including these mixed monotone decompositions, to do state estimation in the space of intervals, get the estimated sets, and then return back to the original polytope space. So with this idea, now we were able to do polytope-valued state estimation. And as you can see, for example, just to illustrate it, the combination of these zonotope bundle-based decompositions and constrained zonotope-based decompositions really outperforms the estimates, the polytope-valued estimates obtained by some other benchmark methods in the literature. Okay, this was more or less what I wanted to talk about regarding the applications of mixed monotonicity in state estimation. However, now you might ask this important question that after computing this reachable set or set-valued state estimates, is there any guarantee that they remain bounded or stable through time? And this brings the notion of set-valued observers, and in particular, interval observers. And now we want to see if we can apply some ideas from this mixed monotonicity to design interval observers. So yes, now the question is, given this nonlinear system with nonlinear observations, we want to synthesize these upper and lower framers. We want them to stay uniformly bounded or stable, and we want our design to be optimized. More or less all the criteria that an interval observer should satisfy. So I know that there have been, and you know better than me, there have been a lot of nice efforts in designing interval observers, including from some of the people in this community. So it turned out that using these embedding systems and decomposition functions, also we can contribute in this interval observer design literature. Okay, so what is the main idea? The main idea is to do that decompositions on both state equation and observation equation, turn them into linear terms over state and noise, and Jacobian sign stable with respect to state and noise, and also add this zero term, which is zero by construction from the observation equation, times this now design factor L, or observer gain to be designed L, right? From these three, we get an equivalent representation of the original system, which is by construction now decomposed into two system components. One that is linear over state and noise, and the other one which is nonlinear over state and noise. Now we can apply that idea of embedding system separately on each of these components, this linear system component and this nonlinear system component, compute embedding systems for each and add them, and then compute an embedding system for the original system like this. This, by construction, returns frame for the original system, and what remains to do is, as usual, compute the errors of this system, and then design L in a way that minimizes some norm of the error system, some like one norm or infinite norm, and that gives the optimal L in the sense of H infinity or L1. All right, so to summarize, given some conditions, some mild conditions, some like local ellipticiousness, which implies bounded Jacobians, we have mixed monotonicity, and the existence of these embedding systems are there. Then by solving some semi-definite program or mixed integer linear program, we're able to design optimal gains in the sense of H infinity or L1 norm. And then this design is applicable to both continuous time and discrete time systems, because embedding systems and mixed monotone, the decompositions can be computed for both continuous time and discrete time system. And just to illustrate it, if we apply it, we applied it on several examples, including this. And then, as you can see, the framers outputted by our design, these red framers and these black dot framers. Reds are based on MILP. Reds, the blacks are based on minimizing H infinity norm. Both are tighter than the ones that outputted by some benchmark method in the literature, these blue lines. And then it can be also seen from the computed error, observer error. All right, now after talking about the applications of these decomposition functions on interval observer design, is the time to invite adversarial agents to join the game and talk about resiliency a little bit in cyber physical systems. So specifically, we want to see if on top of usual bounded disturbance and noise, if we have some like malicious agents that can inject unknown signals, adversarial signals on both sensors and actuators, can we still simultaneously obtain guaranteed estimates of our state and also possibly compute some estimates of these adversarial signals and try to mitigate their effect. This is the main question here. So to put it in a formal mathematical way, we have our dynamical system, which on top of usual uncertainties, which I talked before, this W and V, now we have these unknown input signals, dk, and then the difference between these, the main difference between these unknown input signal and bounded noise is that we do not assume any prior useful knowledge or assumption or known bounds on the dynamics of this decay. No information. And then we still want to design stable and optimal set-valued input and state estimates. So the main idea is first to apply some singular value decomposition to decompose our observations into two components, Z1 and Z2. It is doable always, such that one of these components are not affected by the unknown inputs, this Z2. Then on top of that, we apply these mixed monotone decompositions on part of the observations, as can be seen. There are other insights here as well. We need to define an auxiliary state in a way that then the dynamics of this auxiliary state is not affected by the unknown input. We also need to apply this mixed monotone decomposition on part of the state equation. And finally, we enter and we use that part of the observation equation that is not affected by unknown input as that feedback term to bring this design variable L as before. Okay, combining all these ideas together, we can design a recursive algorithm, three-step observer design, which of computing input framers, then propagating this auxiliary state, and then computing the framers for the actual states as functions of those framers for auxiliary state. Sorry if this slide is too mathy. I just wanted to put those steps of the design together and highlight in red the places that we use that decomposition functions like this JD and this ROD and this Psi2D are all decomposition functions. Basically, wherever we have some nonlinearity over state, we use these decomposition functions to find bounds over that nonlinear function of state. Okay, with these all together, now we are able to compute the aerodynamics, and then as a result, if some dynamical properties called strong observability hold, then the existence of these decompositions is guaranteed. Also, again, by using some semi-definite programs, we can design optimal stabilizing gain. And then since these aerodynamics can be upper bounded with linear systems in various ways, we end up having different sufficient conditions for stability of this design. So this has been a very recent submission to CDC. We did it for discrete time systems, and we are on our way to do it for continuous systems as well. And I was honored to collaborate with Tak, who is usually here, one of the audiences in this like seminar series in this work. Okay, yes, and then just to see where we applied it, for example, on a free area power station system, and then as you can see, both state of this system, which are angular velocities and phase angles, and also these crazy unknown inputs or adversarial signals can both be like framed with computed framers nicely. So just to mention, this work and this design had some prior hyperbole-valued type of observer like counterpart, which previously we designed, where we kind of characterized the uncertainty sets as hyperballs with their centers and the radius of the balls. And then we did it for several classes of systems, nonlinear systems, and the relationship between them in terms of the stability of the observer. This was something that we did before, and then recently we got that the idea of that decomposition functions and then applicable to do that interval value type of observers. So one other interesting observation that I wanted to share. So if you apply this framework onto some like this tooling flexible joint robot system, and then compute the guaranteed set estimate, these red intervals, and then compare them with some point estimates, which is outputted by some benchmark observers in the literature, these blue dots and also these black dots. As you can see, because those approaches cannot really handle these unbounded adversaries or adversaries with unknown bounds, then those point estimates will violate these guaranteed set estimates after some time steps. And this can be seen both from the state plots and also from the error, the plots for errors. And this kind of like showcase the significance of this design that we can actually handle this unknown input adversarial signal. All right. And finally, I'm excited to share very quickly the fact that now we are able to do this type of resilient estimation in distributed settings. So we still have a target system, a nonlinear dynamic system, subject to noise and these unknown inputs. And instead of a centralized like sensor or observation, now we have a network of sensors. Each has its own observation function. It is HI, and each of them are subject to noise, measurement noise, and also the unknown input. And then using our previous toolbox, we can, each of these sensors or agents can compute their own local estimates, like interval estimates of the state of the system. Now the question was, can we use some network properties so that they can share these local agents can share their estimates in their local neighborhoods and do some sort of consensus in this set valued setting to make sure that after finite time steps, then they all reach to some consensus over this the estimate of the state of the system, and also this distributed way of estimation refine the centralized way of state estimation. That was the main question. And then here we were able to introduce this notion of min-max consensus, which is a counterpart of average consensus, through this additional new network update step. And that is basically each agent share their estimates with their local neighbors and take the intersection of them. And then you can see that this intersection still is a guaranteed estimate, which is guaranteed to contain the true state of the system, and also if some network conditions, which we call them collective observability holds, then we have consensus after finite time steps. So we got very interesting results for linear systems here, distributed very large scale linear systems, and we are on our way to do it for nonlinear systems using decomposition functions. And we'll talk about some of these results in this coming ACC next week in an invited session on resiliency and privacy throughout cyber physical systems. All right, so this more or less concludes what I wanted to talk about with this main takeaway that leveraging mixed monotonicity along with some other dynamical systems properties such as strong detectability and collective positive detectability, we can design robust reachability analysis algorithms, do attack mitigation, and also study distributed resiliency in cyber physical systems. So, and last but not least, I want to very quickly mention some of the future visions of this mixed monotonicity, which to me is very interesting, and I will be very happy if you are also interested, and we can even do collaborations on some of these. So I would like to apply this mixed monotonicity property along with some other dynamical system properties to go towards hybrid, non-convex, and unknown CPs. So more particularly, it turns out that these decomposition functions are applicable to do hybrid systems reachability analysis. We have some preliminary work there. And because they are applicable in both discrete time and continuous time, we can apply them simultaneously with some complexities on jump times and guard sets and stuff like this, but we are on our way of doing that. Also, in computing controlled invariant sets for general nonlinear systems, they are very applicable there. Moreover, using these like box tightening type of algorithms, we can apply these mixed monotone decomposition functions in design non-convex optimization algorithms and non-convex distributed optimization algorithms. Moreover, I have mainly dealt with set-valued uncertainty models in these settings. And as you know, there have been a huge literature on dealing with stochastic type of estimation when stochastic uncertainty models are considered. So I was wondering, how about if we have both type of uncertainties in these settings, and can we advantage both of them? And then I learned that very recently there have been very interesting work in the math literature on propagation of random sets through mixed monotone functions, which I think is like some of the results there can be very nicely leveraged to do this, and then to see if we can use these random sets as something to address simultaneously both set-valued and stochastic type of uncertainty models in dynamical systems. And finally, I have contributed in some set membership or guaranteed type of learning approaches, data-driven learning approaches in my PhD work, and I'm interested to apply them to learn the dynamics of unknown cyber physical systems, and then apply all these model-based mixed monotone control and estimation approaches, and then I think we are able to deal with unknown cyber physical systems there. So I'm thinking of targeting some of these like works to write proposals for NSF cyber physical systems or NASA NS Pirates Early Career Award in the future. to get funding for these future projects. So with this, I'm gonna thank you all so much again for your attendance. I'm gonna thank my family for all their support, my great PhD and postdoc supervisors, all my lab mates, all the funding agencies that have funded my work so far, and ASU and UCSD engineering schools. Thank you so much, and I would be very happy to take your questions and further discussions.
Okay, then many thanks for your very inspiring presentation. And yes, as you have just mentioned, the floor is now open for discussions. Is there anyone who wants to start? Okay, then maybe let me start with the very first question. At the Outlook, you have mentioned this concept of random sets.
Yes.
Could you give a little bit further details about this concept? Is it closely related to approaches like p-boxes, for example, where you have, let's say, probability density functions? In the Gaussian case, for example, with uncertain mean, and bounded variance or bounded standard deviation? Or is it something in this case like, for example, propagating some confidence regions?
Yeah, it's more like the second interpretation that you mentioned. So you know that there are approaches in doing like distributionally robust type of estimation and control, right? That's one way of addressing a sort of combination of like robust or guaranteed type of uncertainties work and stochastic type of work. On the other hand, you can think of having some compact set, like for example, some intervals which can be characterized with upper and lower maximal and minimal values, x underbar and x upper bar, but those x underbar or upper bar and underbar themselves are random variables, right? So we characterize sets first, and then those parameters that we use to characterize the sets, some of them are themselves are random variables. This helps us to have those these type of things that we are interested to have, because we are dealing with sets, but maybe because we will let those characteristic parameters to be stochastic, then we can take the advantage of those type of like information theoretical results on these stochastic things there as well. That is what I am known of about this like random compact set theory.
Yeah, that's a very interesting concept. And I think for a purely set-based representation, there exists also a similar counterpart. This is, for example, something that the group of Luc Gelin is doing in Brest. What they have is something that is called fixed sets. That means, for example, you have an interval where the lower and upper bound is again described by an interval.
Oh, nice. So then, okay, that additional layer of uncertainty there itself again is a set-valued uncertainty, right?
Yes.
Oh, nice.
Yes, and they have introduced a concept like thick interval, where you have uncertain interval bounds. And what I published also together with Luc is something called a thick ellipsoid. That means an ellipsoid with uncertain shape matrices.
Nice. Yeah, it would be great if you could send like some of those work to me.
I'll do it afterwards, yes.
Yeah. Yeah, thank you so much for letting me know. That sounds very, very interesting, as you mentioned.
Okay, now I see that Pierre-Jean has raised his hand.
Yes, thanks for the talk. I was quite interested in the part where you use this interval mixed monotonicity on polytopes.
Yes.
To know if there is any constraint, is there any case where you cannot apply that to some type of polytopes, or any more constraint on the result if there are some cases where it doesn't give good enough result to be interesting?
In terms of accuracy and applicability and the class of systems that it is applicable, actually no, there is almost no constraint, mainly because these mixed monotone type of systems are a very, very, very broad class of systems. Like, just to let you know, these local Lipschitz systems are a very small subset of them. So in terms of that manner, no, there's no restrictions to my understanding. However, these Polytope-Valued type of approaches that I contributed in developing have its own shortcomings. And the major of them is in terms of computational complexity. And that is mainly because of these zonotopes, bundles, and constraint zonotopes. In each step, the number of zonotopes and the characteristic parameters of the zonotopes that you add will increase. And then because of that, the number of computations will increase. And also you need to do some type of transformation between these two representations of zonotopes, constraint zonotopes and zonotope bundle. That is also computationally complex. So with all these, this is not very efficient, right? This is the main shortcomings of this, and that's why I showed it. If you look here, I showed it until time step like 4 time step. It can go through like I don't know 20, 25 time steps, but after that, like it slows down very, very significantly. Okay, so that is the main shortcoming, and specifically because of that, we have some new ideas of how to eliminate some of the redundant zonotopes at each time step, or how to use other representations of polytopes sometimes to make it more efficient. These are some very new ideas that we're now working on.
Okay, thank you. And just a clarification about these zonotopes bundles.
Yes.
When you convert it and then use the mixed monotonicity reachability, you apply the reachability to each zonotopes, or you apply it once for the polytope, the resulting polytope?
We do it for each zonotope because each zonotope have its own generators where live in their own space. We use it, we apply it for each zonotope, and then take the intersection of all the results there, right?
Okay.
Yeah. Those intersections are computationally very efficient because, like, everything that happens in the space of intervals, as you know, are quite like efficient. As long as things are in the interval representation. Yeah, and those intersections are just taking some like min and max over the frame, like upper and lower framers, right?
Okay, let's see. Do we have any further question in the audience? Yes, if not, I have a further one. Where you introduced the linear remainder term, do you have any, let's say, recommendation in the case where your linear term would efficiently be described by an interval matrix? How to parameterize or how to optimize, let's say, this representation hx plus g of x? If yes, you could determine, let's say, a system that has linear dominant behavior, but this matrix H would efficiently be described by a bounded matrix. For example, parameter uncertainty. You have constant but unknown parameters included in your system model.
Mm-hmm.
And then you could use this representation. You could either shift this interval uncertainty to the matrix H, to the green term, or you could shift it to the blue term, to the term G.
That's a very interesting question, and actually we have thought about it before. One way of doing, like, handling those uncertain parameters in the system is what you just mentioned. However, that might bring, in some cases, that might bring in overly conservative computations, because you have like two uncertainties multiplied together, and then, as you know, that might end up getting like very conservative bounds. Another way of handling that, which we did in some examples in this like TAC paper, is that you just consider those uncertain parameters, interval valued uncertain parameters, as some variables, some state variables in f of x. Let's say you have f of x and delta, where delta is your uncertain parameters and x is your usual state. So if you consider x, the augmentation of x and delta, call it like z or zeta, then you have, technically, you deal with that delta as one of those like x's. And then all you need to do is then now you have to find a higher dimensional h based on higher dimensional Jacobians of your function. But now this Jacobian, you take Jacobians with respect to both state and parameter, right? And then do whatever I show here, but with new h's and new g's and new Jacobians and new derivatives, right? That's another way of doing it. So based on my experience and the simulation results, this way, most of the time, turns out to give much tighter and more efficient type of like reachable sets and tubes.
Okay, then this would be something like, yes, let's say the classical augmentation of the state vector by integrated disturbance models that represent the uncertain parameters.
That's right. That's right.
Yeah. Okay, then let's see once again. Last chance for the audience to ask questions. Otherwise, I can only just advertise for the fact that Mohammad will definitely send me the slides. We'll put them on the webpage, that you can also go through all the references again. Many thanks again, Mohammad, for your presentation. And yes,
it has been my pleasure.
It has been a great occasion to have you as at the moment, last speaker before our summer break in the seminar series, and I'll let you know as soon as we're restarting the seminar series by the end of September.
Sure. Thank you so much again for your invitation, and hope we can meet you soon in person somewhere.